Hi everyone, and welcome to this technical session on ROPS and FOPS analysis. I am Spa, and I'll be presenting this technical session today, and the main focus will be on ROPS and FOPS analysis. I'm an application engineer at Qfinsoft. We provide training, support and consulting on Ansys products, and we are a certified an Ansys authorized channel partner. And we'll be looking at practical guidelines within Ansys Workbench for ROPS and FOPS analysis. We'll mostly be working in Ansys Mechanical on the ROPS part, and then for the FOPS, we'll be working in the LS Dyna Workbench version. Okay, so here's a session overview of what we will be going through today. So firstly, we'll do a quick introduction on ROPS and FOPS analysis, and then we'll look at the relevant ISO standards for ROPS and FOPS tests, and then the simulation workflow you can follow when doing ROPS analysis, which will be an Ansys Mechanical inside of Workbench, and then the simulation workflow that you'll be looking at if you're doing FOPS analysis inside of the Alice Dyna Workbench version. And then we'll have a quick demo at the end. Okay, so what are ROPS and FOPS? ROPS stands for rollover protective structure. It is designed to protect an operator in the event of a machine rollover, something especially important in uneven and unstable terrain. It's typically a reinforced cab frame that has to withstand rollover forces without collapsing into the operator's space. And then for the FOPS is the folding object protective structure. And then while ROPS protects from ground level rollovers from unstable terrain, FOPS deals with overhead risks such as falling rocks, tools, debris, trees, and stuff like that. You'll commonly see this in mining and forestry machinery, and then the goal of the FOPS test is to keep the operator safe by limiting intrusion into the operator space, or what's called the DLV, the deflection limiting volume, uh, and then the relevant ISO standards for ROPS and FOPS. So for ROPS, we have ISO 3471. This covers static testing for ROPS, checking how structures handle force in various directions and how much they deform during the rollover process. And then ISO 3463, this introduces a dynamic rollover test, more realistic, and simulates an actual machine tip over. The structure must not breach into the deflection limiting volume. This is where the operator will be sitting. And then for FOPS, we have an ISO standard 3449. This defines an impact test using a falling object. It sets two levels of protection and limits deformation into the operator's volume. And then we have 8083. It's similar to the previous one, but applies to forestry machinery and includes different object masses, shapes. In mining, we usually align with ISO 3471. That's for the ROPS test, and then 3449 for the falling object test. Okay, and then this just quickly shows a slide of going more in details over those relevant standards. We can see for 3471, uh, this outlines specific performance requirements, such as how much energy the structure has to absorb during a rollover situation, and then the sequence of how the test gets conducted, of how the forces get applied, and how much force needs to be applied during the testing in the three different directions, which is lateral, longitudinal, and then a vertical case from the top, and then the energy absorbed in the lateral direction needs to be needs to be evaluated within this test, and then this sets a limitation on the deflection under the loads. So meaning that during this loading, uh, no deformation needs to enter that the deflection limiting volume. And then we also have the standard for 3463, which is a dynamics ROPS testing, but we'll be focusing more on this 3471 going forward. Okay, and then we have the relevant standards for the following object protective structure. So 3449, this is usually for earth moving machinery. This specifies test procedures for falling objects, impact on the operator cabins, defines 2 levels of protection, so level 1 low risk and level 2 high risk, depending on the object that is falling on the cabin that has to protect the occupant. This uses vertical impact test with a rigid object, typically a steel ball, and limits allowable deformation into that deflection limiting volume where the operator will be. Okay, and then we also have a standard 8083. This applies to self-propelled forestry machines with operated cabs. So using a falling object to impact as an impactor, and then we evaluate the structure's integrity and deformation control. So looking at how much the cabin deforms after an object has landed on top of the cabin, and if this cabin ends up inside the volume of the occupant, then it's unsafe. And then this ensures cab integrity protections of the DLV during and after the impact. Okay, so first we'll be looking at how we can handle looking at testing cabins or machines for ROPS inside of Ansys Workbench using Ansys Mechanical. So for this case, we'll be looking at the standard of ISO 3471 for the static ROPS testing. So the first thing we'll need to handle when looking at ROPS inside of Ansys Mechanical is our materials. So usually the materials we'll be working with are non-linear materials inside of a static analysis, and then we need to define these materials inside of engineering data. While you're inside of engineering data, as shown there, we can define the plasticity of the materials that are used inside of our test, and then we can define a rigid body deflection limiting volume of where the occupant can be. We can draw this inside of Discovery, or we can define this inside of Discovery and then set a material for it, and then we can define some kind of contact between this volume and the volume of the cabin, so that we know at what point we could have the cabin intruding into the volume of where the occupant will be seated. Okay, so after we've set this part up, the next important part is the settings that we'll be using inside of Ansys Mechanical, and the loads that we will be defining for our ROPS test. So usually for this kind of test, it'll be a non-linear analysis, since we have a non-linear material. And then for this, if this is the case for any non-linearities, we need to turn on large deformations inside of our analysis setting. And then for other cases where we would need to turn this on would be cases where we have non-linear contacts. We have geometric non-linearities, so a lot of deformation inside of the structure that we have inside of mechanical. And material non-linearities is the case that we'll be turning it on for, as we defined our material earlier. And then for ROPS, 3 forces need to be applied and released sequentially, as it would be done in a test situation. So first we have our lateral, so that will be from the front. An example is like of a crash. So from the front, and then no, sorry, lateral from the side, and then longitudinal will be the crash case from the front, and then finally we will have a vertical load, and then the size of these loads depend on the mass of the structure, and then the ISO standard would recommend the the size of the load that you will need to apply these forces in. So as we will be applying forces and relieving them, it's good to look at having a multi-step analysis. So also inside of our analysis setting, we can turn on 4 steps for this case. So we'll have 1 step for the lateral load, one step for the longitudinal load, and then one step for the vertical load. And then I've added an additional 4th step. This is where all the loads have been removed, and we can see the final deformed state of the cabin after all these loads, as would be done in a test. And then non-linear material will ensure that if we have any kind of permanent plastic deformation occurring in any step, they will be kept into our following sequential steps. Okay. And then so using the defined load steps, we can go and apply these loads on our cabin. So we can see for each step where those loads are being applied and the time step that it's being applied at. So for the first one, we have it being loaded on that first time step and then relieved at the end. And then for the second one coming from the side, it's loaded in the second one and then relieved. And then finally from the top. And then in the final load step, that last load is completely removed, and we can see the final deformed cabin from those steps. And then after we have solved our ROPS inside of mechanical, we can go and obtain our graphical results. And then a good tool to use on this side is being able to see that shadow of where the cabin used to be, and then the colored part is where the final deformation is. So one important aspect of doing the ROPS and a standard that the cabin needs to comply with is how much energy the structure absorbs during one of the loads. So you can go ahead and plot that. What you can do is inside of mechanical under our solution, we can go to the worksheet, and then we can under the worksheet we can retrieve results for our displacements, and we can retrieve results for the forces being applied. Those results can be tabulated, and there I went and took the net force and the net deformation. We can go and paste those into something like Excel, and then plot our force versus displacement. And then from there, depending on which load we need to calculate our energy absorbed for, we can go and take those deformations and those loads or forces, and we can go ahead and plot those. And then by calculating the area underneath of the graph that we get at the end, we can determine how much energy the structure is absorbing during all this loading, or during a specific load that the ISO standard wants us to comply with. Okay. And then moving on to our FOPS analysis. So for the FOPS, falling object protective structure, we'll be looking at doing this kind of testing or analysis inside of Alice Dyna. So there's a Workbench version of Alice Dyna. If you're used to working inside of mechanical, it'll be much easier to set up in here. So the reason why we go to Alice Dyna is we're looking at an impact kind of analysis, and for these short duration analysis, we look at an explicit solver such as Alice Dyna. So also if we had to do these tests in a sequence, or after completing our ROPS, we can go ahead and put our Alice Dyna in the same Workbench, and then we can connect the branches that we need in our FOPS. So in this case, we already have the geometry that we tested for the rolling over, and then we can go and connect that over into our Alice Dyna. And then if we had some engineering data for materials that we may have created in our earlier static structural analysis, since they already have non-linear properties, we can go and use those inside our LS-Dyna falling object protective structure analysis. And then from there, inside of the engineering data, we can go a bit into more details. We have more models, material models that we can look at inside of LS-Dyna, depending on the material that we have and the kind of testing that we're doing. We can go and simulate stuff like if the impactor actually breaks the structure, we can set a criteria for when it breaks, and then we can insert some kind of breakage model inside of this test. Okay. And then this quickly shows the workflow of how we'll be going in our FOPS analysis inside of LS-Dyna. So after we transfer that geometry over, one thing that we'll need to do based on the ISO standard, it'll tell us what kind of an impactor we would need to use on our cabin. So we can go into Discovery and go and draw up that impactor. And then from there, that data will be transferred over into our LS-Dyna environment. And then from there, we can start applying our boundary conditions. And then finally, after our run is completed, we can go and post-process these results. Okay, so going back to the start, after we've transferred over our geometry, we can go into Discovery and go and define our impactor based on the impactor that the ISO standard that we're looking at wants us to use. And then for the impact test, we have the cabin and the impactor starting at a position where they are touching. This is ideal, so we don't have to waste any solving time computing for that impactor falling onto the structure. So basically all we do is we put the impactor and the cabin already contacting, and we define a falling height for the impactor, and that workbench or LS-Dyna workbench goes back and works out the velocity of the impactor, and then that's where the simulation will be starting. Okay, and then so after, if we go into our LS-Dyna environment, we'll see that the impacts and the geometries, if our impactor and other geometries are not of interest, we can go and convert those into rigid bodies. This will save memory on meshing and save solving time, since we'll have a less dense mesh, so less nodes to calculate at. Where possible, another modeling approach we can use is modeling parts as mid surfaces. So in this case, we have our cabin here modeled as mid surfaces. This will optimize on the size of the mesh and then how long our solve will take to complete. And then afterwards, when we've imported all our geometry in, and we've defined all our geometry as rigid or flexible depending on what we want to look at, we can go ahead and start applying our boundary conditions into our system. So in this case, we can go and apply a drop height for the impactor, which will be converted into an impact velocity, and then the simulation will start with the impactor hitting the cabin at that velocity that is calculated back from the height that the impactor is dropped at, as we can see there. Okay, and then FOPS and LS-Dyna Workbench are post-processing. So after we've run our simulation inside our solution information, we can go ahead and insert our kinetic energy and internal energy, and make sure that we have a force balance within our system and nothing weird is happening. And then the model can be inspected for breakage and deformation to determine if the structure is safe per the standard, or if we have any intrusion into the volume where our operator will be. And then we can go and animate this as we see as this impactor is falling onto our cabin. We can see that we have some breakage occurring on the cabin, but we don't have any protrusion into the cabin where the so the impactor doesn't fall through and crush our operator. So we can go ahead and post-process stuff like that. Okay. And then that's pretty much it. From here, we'll quickly go into how we set up these simulations inside of Workbench. And for this case, we'll be looking at the a ROPS demo. So I have our Workbench environment set up here, and I've already done a few tests. So here we have our ROPS analysis, where we have went and mid-surfaced that cabin. So I can quickly open the geometry here, and you can see how the geometry is created inside Discovery. Okay, so this is the geometry that we used for our cabin in the ROPS test. You can see here all these beams. I've gone ahead and mid-surfaced them. Yeah, so if you go here and you show all, you can see that originally these were solid beams, and then all that we did was cut them up and then mid-surface them, and then at the end we end up with something like this, where we have these mid-surfaces, and then between these mid-surfaces we have the topology shared, so that they behave as if they're one solid structure that's bonded. So if we go under here in prepare, we can go ahead and review that those edges that are shared together. So we can see this all will behave as one structure after the topology has been shared. And then we could go ahead and close this and head over onto mechanical. So jumping back into Workbench, we can double click here on the model, and then that will start opening our mechanical model. As you can see down here, it's starting. Okay, and now it's open here on the mechanical side. So we can go ahead, and the first thing that we will need to do, we have a top-down working approach. So what we'll do is go inside our geometry, and then inside our geometry, we'll define what we want to be rigid. We'll set it to be rigid. So in this case, I've went and set this bottom part to be rigid, and I've set it as a structural steel. And then we have all these other parts, which are basically all these mid-surfaces that we created here for the cabin, and we'll have those as flexibles, and they are shells. And then from being prepared on the Discovery side, they already have a thickness set to them. So the one that I'm currently hovering over has a thickness of 5 mm. And then from there, our material is set up for this analysis. We can go and review this material here inside under materials. So it was set to the structural steel, a nonlinear structural steel. And if we scroll down here, we can see all the properties of the steel and this other one, and we can see that the steel has a bilinear isotropic hardening. So as the steel is deforming, if it goes into the plastic region, it'll incur some permanent deformation that'll be carried on from the current step into the next one. And then the next step we'll want to go into is our contacts. So basically I only have one contact here, since these are two separate bodies. All these mid surfaces are already considered as bonded together, since we went and shared the topology between them. As we'll see in the mesh, we'll have a conformal mesh going from one sheet, from one plate to the next one. So the only contact that we needed was just fixing our cabin onto this bottom part where the seat will be and the operator will be. And this will be a bonded contact. And then afterwards, we can go into our meshing. We can quickly generate a mesh for this cabin. So where the mesh will be generated is on these shell bodies, and also on the contact surfaces where we have our contacts between the cabin and the bottom part. We can go ahead and show that mesh here. So you can see we have a very simple kind of mesh due to modeling approach that we went for by using mid surfaces, and then we can go and refine this mesh later depending on the kind of results that we get back. And then we head over back into our static structural now. So we'll be setting up our boundary condition and the loads and how the analysis will be carried out. So the first thing to look at is going here into analysis setting. We've gone ahead and set the number of steps to 4. So we have 3 for each of the loads that'll be applied, which will be longitudinally, a frontal impact type of loading, laterally from this side, a side impact, and then we'll have a vertical load at the end. And then from there, another boundary condition is we need our structure to be fixed as it would be in a test scenario. And then from there we can go ahead and start applying our forces. So firstly we have this longitudinal force. We can go ahead and turn off this mesh, so we see we have a force being applied here from the front, and then this force from here we can see is being applied in our first step in our analysis. And then our next step, lateral from the side, will be applied in that X direction in our second step after that first force has been relieved. And then at the end this force gets relieved and we get a vertical force being applied from the top. So after we've set all this up, the other important thing is, since we are working with a non-linear simulation, we need to have our large deflections be on, as you can see there. And then from there, we can go ahead and run this, and we will have our results in a bit. So I can go ahead and pause. Okay. So as our simulation is running, we can go and track our convergence in here under solution information. And we can see what's happening for each step as they're converging. It might struggle at a few points due to this being a nonlinear simulation. It's not that straightforward. And then while it's also solving this, we can go ahead underneath here and insert things like our deformation plot trackers, stresses and strains that are being plotted as the model is busy solving. So here we can go and update this result, and we can see what's happening to our cabin so long while our loads are being applied. Okay, so there our first few forces have been applied, or the first force thing is still being applied, and now it's gone into the second part, and we can see the deformation so long that's already occurred on the structure. So from that force we can see that our cabin is bending this way, and then based on if this deformation there's any plasticity happening, that will be retained for the next step. And now that our analysis has run to completion and we can see all the steps there have converged from all the loads, and then the final load where all the loads are relieved from our cabin or structure, we can go and post-process results. So we can go ahead and click here on insert. We can look at the deformation, stress. We can post-process strain energy of our cabin as it's being loaded. So we can go and look here, the ones that I've already put in for deformation. So you can see a shadow here of where the cabin started, and then after our 3 loads, where it has ended up happening, where it has ended up landing. So we have the pushing force from this side pushing it back, so we can see it's deformed this way, and then we have a lateral load that pushes it one way this way, and then we have a vertical force that gets applied from the top. And then all these forces, based on the standard that you're following, will be recommended based on the mass of the structure, and then a sequence will be given to it on how these loads, in the sequence that these loads need to be applied in. And then afterwards, one of the criteria that needs to be fulfilled for the ISO standards is the amount of energy that the cabin or structure absorbs during a certain loading. So we can go ahead here into solutions, go into our worksheet, and then from here we have some custom results that we can go and post-process. So what we need to post-process from this side for the ROPS test, we need a graph that shows the force over the displacement over while the force is being applied. So we can go and plot this some displacement here, and then we can go ahead and plot uh, the net force here as it's being applied, and then we end up with these two results here. So you can see from here it gives the maximum displacement over time, and then here it gives the net force over time. We can go ahead and click here and copy these over into something like Excel, and then we can go ahead and plot our force over displacement graph like we saw earlier in our presentation. We go a bit back. To there, and then we can see there from the worksheet we can go and get that force versus displacement, and we can plot it on something like Excel, and then working out this area under here gives the energy that the structure absorbs during loading, and then that needs to be a criteria that is met under those ISO standards. Yeah, and that's pretty much it from this side of the ROPS demo. And returning here to our slides. Okay, so we've reached the end of the presentation. We've seen how we can set up our ROPS and FOPS inside of Ansys in the Workbench, in the Workbench environment, and how we can link our ROPS and our FOPS if we're testing for the same structure, so we don't have to do any repetitive work. We can just carry over what we did earlier in the first analysis, and then take it over into our FOPS, and then do a few tweaks, and then run that test as well. So just to summarize, ROPS and FOPS are critical for safety in many industries, like a mining industry. Ansys Mechanical is great for static ROPS simulation, like we've just seen from the demo. Very easy to set up and solves quite quickly, as we can see from the test that we ran just a bit ago. Using our mid surfaces, this only took about 3 minutes to solve completely, and we have our results there, and then we can go and do iterations based on if we need to improve our structure. And then LS-Dyna, or the Workbench LS-Dyna, handles dynamic FOPS impacts very well. It's easy to set up if you're used to the mechanical environment. All you need to do is go add your impactor, and then from there you add your boundary conditions, such as the drop height of that impactor, and then LS-Dyna Workbench automatically converts that for you into a impact velocity. And then the ISO standards that we looked at earlier, these guide our setup and evaluation, especially with the deflection limiting volume as a key safety criteria. So we don't want any intrusion into where our operator will be sitting. And then combining these tools helps to ensure compliance and robustness in the design of our cabins in these areas. And then, yeah, so that's that from the ROPS side. And then finally, here we have some contact information. Thanks for watching. If you have any questions, feel free to contact us using the info shown here. We have a email, info@qfinsoft.co.za, a website, and then also a telephone number. For any questions related to Ansys software, you can contact us on that. Yeah, thank you very much for watching.